This is part 8 of residential air system design. In this video we're going to look at part H on the worksheet, which is sizing of return grills, branches, and main trunk ducts. Start by placing all of your individual rooms where the return airs are located, and then indicate the return letter for that room. Now, just a quick note before we move on. Just a reminder that a 2x4 wall has a plate opening which is equal to a 7.5 inch round, and a 2x6 wall has a plate opening that's equal to a 9.0 inch round. This is important because our table for air friction loss is based on round ductwork. And once you know what the round size is, we can then find the equivalent rectangular duct. And so table C5 is all for round ductwork, and so that's why we need to know what the round size is. So moving ahead, row H4, H5, and H6, we can't actually fill them in yet because we need to do some additional calculation. The inlet pressure loss is determined from your grill manufacturer, and in the case of our grills, we have a pressure drop of 0.02. So this is an average pressure drop, and this would apply to any grill that's a steel pressed grill. So you can add the inlet pressure in row H7. Now note that for R2, which is the basement, there is no grill there, and so that's why there's a 0 on the pressure loss. The next row, H8, is the return plenum pressure, and that is obtained from part G. Here's your return plenum pressure. This pressure will apply to all the returns. It doesn't matter how many returns you've got, it will apply to all of them. The next is your adjusted pressure. You simply subtract the inlet pressure from your return air plenum pressure to give you the resulting adjusted pressure. Then you need to insert the branch effective lengths, which come from part F, and all the branch effective lengths are what we calculated a few steps ago. Once you have got these effective lengths in place, you can find your loss per 100 feet. And the formula for that is you take your adjusted pressure times 100 divided by the branch effective length. So if we look at the calculator, if we take 0.12 times 100 divided by 227, we get 0.029. So if we start rounding, that's 0.0529, so that's 0.053, and at this point we would just round down to 0.05. That gives us our loss per 100. Now we know that R1 starts in bedroom 4, and on the second floor we know that that is a 2x4 wall, and therefore the round branch size is going to be 7.5. So now that we know the pressure loss and the duct size, we can establish what the actual air volume is going to be. So we enter table C5 at 0.05, and we come down to meet 7.5 inch round, and we can see that at this pressure drop we can carry 132 CFM. So we can add 132 CFM as our inlet flow rate. Now, because we've got a grill going on here, we want to find out what the minimum free area of the grill is going to be. And so you go to table C8 and we look for 132 CFM. In this case, you can use the normal rounding. So 132 rounds down to 130, which means that we need a grill that has a free area of 47 square inches. And so 47 square inches can be put into our worksheet right here. Now you need to flip back to your grill page and you find out which grill gives us 47 square inches. So we can see we've got 41 square inches and then we've got 51 square inches. And so we need to go with 51 square inches, which would be a 10 by 6. And there's our 10 by 6 return grill. Finally, the branch rectangular, because this is a 2 by 4 wall, the branch rectangular is effectively the size of the stud space, 14 by 3.5 inches. Now if we look at R2, R2 is the only return that we actually know the air volume prior to this calculation. There's a rule that says for the basement you can only return 50% of what you supply. And so in this case we're going to be able to return 82 CFM. We've calculated our pressure drop so that at 0.07 and 82 we end up with a 6-inch round duct. Now the basement inlet size, I've suggested that a height of 4 inches is the normal height size. So you want to just double check back here on page C6. We've got a 6-inch round, and so we want to find the equivalent of a 4-inch deep, and we see that it's 8 by 4. So we can put our 8 by 4 or 4 by 8 inlet size for the basement right there. Now if we look at the fourth return and the fifth return, we're going to follow the same procedure. Again, because the return airs are originating on the second floor and they are originating in a 2 by 4 wall, our branch duct is 7.5 in both cases. We've calculated our effective loss here, and so when we enter the table C5, we can find that at 0.06 and 7.5 we can return 147 CFM, and for R5 we've got 0.07 and 7.5 we can return 159 CFM. So that leaves us with 147 CFM for R4 and 159 CFM for R5. At this point, we know that the total design airflow rate is 710 CFM. So we've been able to establish these 4 returns. All that's left is the dining room return, R3. To establish the amount of return air for R3, you would simply add up the 4 returns that you know, and that gives us a total of 520 CFM. Simply subtract 520 from the total airflow rate of 710, and that leaves us with 190 CFM. So based on the other 4 returns, the dining room return needs to bring back 190 CFM. So based on 190 CFM and 0.07, we can look at 0.07 and come down and find that we've got 188 CFM right there, and that is equal to an 8-inch round. Now we know that a 2x4 wall is equal to 7.5. The dining room is on the first floor, and the first floor wall is 2x6. So we know that we've got a 14 by 5.5. So at this point, we can determine that we only need a single stud for the dining room return. Now, initially, we had suggested that we would require a double return for the dining room. But as you can see, the calculations have shown us that we only need to have a single returner in this location. So once you go back to your drawing, you would rework this to only show a single stud return in this location. Now that you have established all of the airflow rates, we want to look at the return duct system. And we can see that we're proposing a section of ductwork to carry the volume of R1, 2, and 3. So we need to find how much air is going to be in this particular duct. So we start off by bringing our first air volume down to the trunk flow rate, 132. Then we add R2 to R1 to get 214. And then we add R3 to R1 and 2 to get a total of 404 CFM. The next thing we need to do is look at what is the lowest pressure drop for those three returns. And if you come here, you'll see that we've got 0.05, 0.07, 0.07. Therefore, the pressure drop for R1 is the lowest, and so it's going to be the determining pressure drop for our duct size. Now we can go back into table C5. Under 0.05, we're going to scan down and find 404 CFM. In this case, we've got 423 CFM. That's our nearest airflow rate, and that is equal to an 11.5-inch round duct. And so we can put in our round trunk duct size here at 11.5. Now we want to find the rectangular equivalent. So you would go to table C6. You would look up 11.5-inch round, and you would scan across to 8-inch deep ductwork. 8-inch deep ductwork is the industry standard, and so this is typically ductwork right off the shelf. And we find that we've got a 14 by 8 duct required to carry that volume. So the actual rectangular equivalent is 14 by 8. Now they're asking for the installed trunk size, and because ductwork is manufactured in increments of 2, 14 by 8 would be a standard duct size. 13 by 8 or 15 by 8 is typically custom, And so unless you have a very specific reason to go with an odd size, you would simply choose the size off the shelf. In this case, the 14 by 8 is a standard duct size, and so that would be the size that is going to be installed. For the trunk velocity, the formula is listed here. You simply take the air volume, so you've got 404 times 144, and then you're going to divide it by the area of your duct. So in this case, because it's all multiplying and dividing, we can simply divide by 14 and then divide by 8. And we end up with a velocity of 520 feet. So now we know that we need a 14 by 8 duct for this section here. Finally, we want to size this return section, and so this return section must carry the volume of R1, 2, and 3 plus the volume of R4 and 5. So in other words, in this example, this portion of the duct must carry the total design airflow rate. So in that case, we've got 710 CFM at 0.05. So we'll go back to table C5, enter the chart at 0.05, and we're going to scan down and look for 710. Here is 707, so that's very, very close, so we can go with that. And you can see that that equates to a 14-inch round duct. So 14-inch round duct would go right there. Now you flip back to table C6, and you're going to look up a 14-inch round and come across, and we see that a 14-inch round is equal to a 22 by 8. And so we can add our 22 by 8 onto the worksheet in row H18. Now once again, row H19 is looking for an installed trunk size. 22 by 8 is a standard off-the-shelf duct size, and so we would simply use that as the installed size. Once again, to find the velocity, you take the airflow of 710 times 144 and just divide it by 22 and then divide by 8, and we get 581 feet per minute for the velocity for this ductwork. Now at this point, we also need to determine what the drop duct size is. And so the drop duct is, of course, this duct which is carrying the total volume of air. So in our example, because this section of ductwork is carrying the total amount of air, and we found it to be 20 by 8, in this example, we'll end up with the same duct size for our drop duct. But it is important that you establish what the drop size is going to be, because it is possible that the drop size could be larger than the trunk ductwork, particularly if you've got return air coming from two directions.